appreciate it. I decided not to record it so that if you have to come back and rewatch this lecture, you can just get right into the good stuff. Because I've found that when I do record it, all you hear is me talking with these weird gaps of silence in between. So, like I said last week, I'm going to be doing my best to record these lectures. I haven't posted our first lecture onto YouTube yet, but later today I'll upload this one and last week's onto YouTube. Some of you might find that having it on Canvas is super easy. Some of you might find that YouTube just has better features for you, so use whichever one is easier. Remember, it's not required in any way. It's just me trying to give you that benefit of having it. In the last week, you guys have probably had some time to dig into the course a little bit. Have you felt confused? Can you put words to any of the confusion that you've had about how you're going to navigate the course this semester? What feels like it's tripping you up? No, it's not as clean as one module every day. It's it might feel that way, but it's not cut and dry. So I think today we should be able to get through most of Module 1. And next Monday, we should be able to get through most of Module 2. I do find that, especially in the earlier chapters, we can go through a module pretty quickly. But it's not exactly. And you all may have noticed that RealChem has a suggested timeline for how you complete assignments, and Canvas has that calendar timeline, and they don't exactly line up. And it's challenging to get them to line up. RealChem automates that, whereas Canvas was kind of placed in its order by the course lead. And so that's kind of the expected timeline, but some sections are going to deviate. For instance, his sections meet Tuesday, Thursday, so they've had 3 classes already, and we're just having our second. So it's challenging for it to line up perfectly, but I would like for you guys to think of those as kind of like timeline windows, right? Canvas and RealChem are kind of giving you a window of when to expect to do these assignments, and you don't have late points for turning in things past their due date unless it's a unit test or a midterm. But I will do my best to stay on you and use the gradebook feature. I can say message students who haven't submitted, and I'll just send a mass message to say, make sure you are staying on track with your assignments and start turning this stuff in. I don't want you guys to fall behind. When it comes to the pre-reading quizzes on Canvas, the idea is that you've done the reading and then you've come back to take that quiz. And ideally, you do it before you come to class and learn that material so that I can clarify questions that you might have. Otherwise, I start talking and I bring up questions that you never had before, and then you go home and you do the reading and the pre-reading quiz, and you still have those questions because you haven't had anybody to actually explain it. So the idea of the readings and the pre-reading quizzes is to get you to do them first and then come back. But you're not going to lose any points for doing them after, because I do know there are some of you that will feel like you'll gain a better understanding in class that you can apply to the quiz after class. So feel it out, find out which method works better for you. Anything else about the class dynamics that you guys want to ask about first before we really dive in? Okay. Sing.
The discussions, those ones aren't required, right? Unless it's the 5-minute notes.
There are 2 discussions that are required, right? The Unit 1 discussion, which I think you guys should probably start doing this week or next week. I'll look at the due date, and is it already due? it shouldn't be impossible for you guys to do it, but I do want to remind you that you don't have to do those Feynman notes on the entire unit. You're picking a topic within the unit that is challenging to you. And remember, the Feynman note process is write down everything you know about that challenging topic. Go back to your sources and figure out what you missed and what you got right. Then return and redo that process of writing down everything you know. And then return and repeat until you feel like you've mastered it more. So you maybe have skimmed through Unit 1 already, hopefully, because we're about to dive into it. Or at least not Unit 1, but Module 1. And you probably have found a topic that you already feel confident on and a topic that you feel a little bit confused on. Take that confused topic and write your Feynman notes. Unit 1 and Unit 2, which we'll be covering over the next 2 weeks, those are due as the online discussions. But everything after that you won't have to do. I'll see if I can unpublish them. I'm really not an expert when it comes to the discussion boards. No, you know what? I'm not gonna disable the discussions, because if you do feel like you have a question and you want to post it to the class, use the discussion boards for that. Or if you find a material, a resource that you really like that helped you in one of the units, post it to the discussion boards. Not required, not graded, except for Unit 1 and 2, but there as a place for you guys to post and communicate if you want to. Thank you. Okay. Well, let's dive in to some chemistry. One thing I'm going to try to do this semester is lay out for you what the textbook says our learning objectives are in each of these modules. So why are we talking about this? What do I want you to be able to do by the time we're done with it? I guess maybe I should say, what does the textbook think you should be able to do? And that's important because that means you're going to have to do it on your module checkpoints and your unit checkpoints. So we're looking at Module 1, Basics, Concepts of Matter and Energy. And these are some of our learning objectives. Distinguish matter from non-matter. Distinguish physical and chemical properties. I'm putting some abbreviations on there. I do want to take a second to address taking notes in class. I, as a student, appreciated how my instructors gave notes. I think they trained me well on what good notes should look like, and I do my best to reflect that back to you guys. So the notes that I put on the board, I'm intentionally putting on the board. I'm trying to organize them in a specific way. I'm trying to give a mixture of definitions and examples, and I want you guys to copy them down as I put them up, because I'm putting them up for you. Or I want you to copy them down in a way that will better suit you if you think that what I'm doing doesn't quite fit on your page. So I want you guys to be mindful about notes. I'm not just using this as a place to scribble. I'm using this as a reflection of what I hope will benefit you. So when it comes to abbreviations, if there's anything that confuses you, please let me know, because I'm abbreviating so that you don't have to spend too much time writing. These little quotation marks, that's to say repeat what's above it. So distinguish physical and chemical properties. I'm just abbreviating phys and chem and prop to make it easier to write. We're going to be looking at phase diagrams. We want you to be able to interpret phase diagrams. We want you to be able to organize matter on scales. We're going to show equations for chemical and physical changes. Very, very basic introduction to those changes. Very fundamental equations. And then lastly, we're going to be looking at the types of energy. I know that's really hard to see, so I'm going to retire this marker for today. So as you go to your module checkpoint for Module 1, you should find that a lot of it reflects these learning objectives. I want you to be able to check this list off by the time you're done with Module 1 and say, yes, I can distinguish matter from non-matter. I can distinguish physical and chemical properties. I can interpret a phase diagram. So let's start with matter, and let's get a definition for it. What do you all understand matter to mean based on your readings? Good. Anything you guys would like to add to that? Edgar.
Anything that has weight?
Weight. That is a very important thing for us to define. So we're actually going to come back to that and define what weight means in this context. I think this is a pretty well-rounded definition for matter. Takes up space, has mass, and let's also define energy. Actually, in order to define energy, I'm going to put it in context. Changes of matter requires energy. So energy is the driving force for changing matter. And we'll talk about how we can change matter. So will you guys help me just create a small list of things that are matter and are energy? Edgar?
Matter is electrons.
Electrons are matter. Good. I'm going to abbreviate electron with E minus. Electrons. What else? Light is energy. Good. What else? Heat is energy. You feel that heat from the fire? That's energy. Air is matter. Good. Takes up space, right? And while it may feel like it doesn't have mass because it's easy for you to move through it, just think about that heavy wind pushing you over. Definitely has mass. Good. What else? Sound is energy. Good. Just like heat, sound needs a medium. Sound propagates through the air. Heat propagates through the air. Heat propagates through a solid. When you grab a hot pan, sound propagates through a solid. I don't know if any of you ever put your ears on railroad tracks as kids. In theory, sound travels faster through solids than through air. And you can hear a train coming from miles away by putting your ear on it. That's great. What else? Vibrations. You know what? I think we can put vibration with energy, and it is different than sound. We're not going to get into it a ton this semester, but when I teach organic chemistry, I talk about how molecules vibrate in very specific ways. The bonds that hold the atoms together vibrate. Sorry, don't mean to distract you with my bubbles. And we can actually take advantage of that. You know what? I don't think we might. we can take advantage of that vibration that these molecules do to actually figure out what that bond is made out of. Actually, I'll just do a shameless plug. I'll talk about this more in the semester. November 24th, I'm giving a talk here on campus on energy from the micro scale to the macro scale. It's part of a series of fun STEM talks that the School of Math and Engineering, the School of Science, Math, and Engineering is putting on. So I'll advertise that for that a little bit more. You guys will see flyers throughout the semester for the different speakers. And I'm going to talk about vibrations a lot more there. Okay, can we get a few more things for matter?
For radiation, I would say for energy.
You know what? Radiation is light. Light is radiation. So X-rays, light. Visible light, rainbows, light. Infrared. If you guys have ever seen heat-seeking goggles, night vision goggles, that's radiation. That's infrared light. Microwaves to heat up your food is light. Radio waves to pick up your favorite songs, that's light. Gamma rays turns the Hulk green, that's light. All of it is electromagnetic radiation. Okay, just one or two more things for matter.
Liquid.
Ryan.
I'd say just
Atoms, good. Any type, any flavor, any combination. And Brian?
liquid.
Liquids. You got a favorite liquid you want to put, or just all liquids?
All liquid.
Got it. All right, I want to point out something about my L there. That is my little cursive L. I don't use it all the time, but I use it a lot with liquids. And that's because we're going to be talking about the state of matter, liquid, quite a bit. And I want it to be distinguished from my capital I, which is often just a line. And I want it to be distinguished from my number 1, which is often just a line. So I'm using a cursive L so that it cannot be confused for anything else. In chemistry, this is one of the hardest things about communicating science to new students. What is a capital I, what is a lowercase l, and what is a 1? So that's what I'll be doing to try and avoid that. Thank you, guys. Now, let's talk a little bit more about what mass is. Anybody have an idea of how to define mass? Mark?
Something that stays constant.
Something that stays constant. You're thinking of the law of conservation of mass. Mass cannot be created or destroyed, yeah? This is good. I don't want to put it up there just because I think we can better refine it, but we're actually going to come back and hit on this idea that you can't create or destroy mass. Cole?
Like how much? I guess quantity, I guess. How much atoms?
A quantity. How many atoms?
I was going to say something very similar. It's the amount of stuff inside of an object.
Good. So I'm going to phrase it this way. This is a measure of the amount of matter. So we might be talking about a specific substance, and we would say this is its mass, and that tells us how much matter that substance has. And a part of mass is weight. Weight is gravity's effect. I always get my A and E effect confused. On mass. So Cole, you have a specific amount of mass, right? And you have a specific weight here on Earth. If you go to the moon, does your weight change? But does your mass change? Right. Mass, in Mark's idea here, mass is a constant. When you transport that item, you're not changing its amount of mass. But when you change its interactions with gravity, you may be changing its weight. So for all intents and purposes, we on Earth often conflate mass and weight because it's really hard to get a mass without knowing its weight. we take advantage of gravity to figure out weight, and then we kind of conflate that to mass. Because you and I aren't often going to the moon where the weight of our matter is going to change. How do we get these weights or masses? How do you know your weight, Alina? That would take a while. What if I wanted to know your mass? Would I need to count up all of your protons, neutrons, and electrons?
No. But I think from the very beginning, we had to have this information, but at ALPHA, we had not a final answer to this question, and that's why we just did a short answer.
Okay. And I might push back and say, I think the first people to ever weigh themselves maybe didn't need to know the sum of all of their protons and electrons and neutrons. But actually, that's maybe a more modern revelation, that we could actually take your mass and we could break it down into, this is how much mass is produced by the electrons in your body, by the protons in your body, by the neutrons in your body.
Are you able to tell it by how much you push down? So because you're able to use gravity's force, you're able to add that together and get your...
So tell me what you would get it on. What's your
Yes.
instrument?
You can do a scale, you can do,
Balance?
yeah.
Good. And is this what you guys were going to add in the back?
Yes.
Yeah? We can use scales or balances to try and get our weight. And then we can infer that that is our mass. You know, in a lot of chemistry labs, you'll say, get the mass of a beaker, get the mass of your solid. And really, we are getting its weight because the mass units that we use on Earth are governed by the gravity that affects us on Earth. But we call it its mass. So if you were working on the moon in a space laboratory, you might have to phrase things different, or you might need to change your reference scale. You might have to say, relative to Martian gravity, this would be a certain amount of weight on Earth. Okay. Anything else you guys want to add to this? Let's talk about what makes up our matter. All of our matter is made up of what we'll call chemicals. This is a pretty vague, broad definition. Because what is a chemical? A chemical is actually fairly large. I don't think that we can say an electron is a chemical or that a proton inherently is a chemical. And so this might be kind of a bigger picture idea of what matter is. And chemicals can be distinguished by two types of properties. Their physical properties and their chemical properties. I want to talk first about physical properties. You know, the difference between physical and chemical is arbitrarily set. We've set it. Well, it's not necessarily arbitrarily set, but there are some things that blur the lines. Those of you that took lab this week or do have lab this week, you guys are doing an experiment on physical and chemical changes, and all chemical changes produce a physical response. You can see only the physicality of it. And there are some that kind of ride the fence. It's hard to know whether that change was a physical or chemical. And I believe that's because nature exists on a spectrum, and we come in trying to slash these lines to it and say, if it falls on this side, we call it this. If it falls on this side, we call it that. Nature doesn't adhere to our definitions. Nature just exists. So we'll do our best to squeeze nature in, and we'll just accept the confusion that comes when it forces its way out. Can you guys give me some physical properties? Brian was so excited for this.
I would say like phase
Good. You know
Sorry.
what? We're actually going to talk about changes in a second. But for now, let's pull it back and say being a liquid, being a solid, being a gas. Those are physical properties. It defines its physical state. So I'll put this up here, state of matter. And we're going to come back and talk more about states of matter. But the state your chemical is in, that's a physical property of it. Danua? Danua. Texture. Is it smooth? Is it rough? Color. Is it blue? Is it white? Edgar?
Oh, I was gonna mention like neon, for example, being a gas.
That's its state of matter, right? And I think I'll put up here gas, liquid, solid, GLS. Alina? Its boiling point. By taking a compound and turning it from a liquid into a gas, you're not changing its chemical nature. You're just changing its physical nature. And so that point at which a compound changes phase is a physical property of it. Boiling point temperature. And I'm going to put etc. here because we can also say the reverse, the temperature at which it condenses. We can say its melting point temperature or its freezing point temperature. There's even sublimation and deposition temperatures. So all of those kind of belong in that same category. That's a physical property it will have. Let's look at chemical properties then.
I would say like formation of a new substance or a new chemical.
So this would be a chemical change is something that produces a new chemical, correct. But what would be examples of a chemical doing that? Caden?
Smell or taste.
Yeah, this actually surprises me. Smell and taste, which are two of your senses similar to texture. Your ability to feel something is just a sense that you have. Your ability to taste or smell something is a sense that you have. But it requires chemical bonding within your body. So you need to chemically change this substance in order to smell it or to taste it. So that makes it a chemical property. Edgar?
Flammability.
Flammability. Here's a fun fact. Flammable and inflammable mean the same thing. I saw that on Merriam-Webster Dictionary's TikTok page. Flammable and inflammable they're not opposites of each other. They both describe something that can take on flames, that can combust. So flammability is a chemical reaction. You are reacting with oxygen and making new compounds. So whether something can ignite or cannot ignite is a chemical property. Right. Color change. Color change is often the result of a chemical change. You have a substance that has this color. Now you have a new substance that has a different color. But I don't think that it's a inherent property, just a side effect. Lizzie? Reactivity. And I like that reactivity with flammability, and we'll see if we can come up with other types of reactivity. So this is kind of a broad umbrella, yeah? Kristen?
What about rust?
Rust is another example of reactions with oxygen. So, like Lizzie said, reactivity.
pH.
pH is actually a physical property. And let's see if you guys agree with me. We're actually not going to deal with pH much this semester at all. Yeah, I think, no, maybe we will.
But pH is actually a concentration. Sorry, I didn't mean to make that all-encompassing. That's a lowercase p, uppercase h, intentionally. So pH is a measure of how much hydrogen ion is in a solution, which is actually a concentration. The concentration just says how much of what is present per total whatever. And that has nothing to do with changing its chemical property, just a physical property. It's what's there. Good thing to add. Alina.
How is it? Do you get acid or bases?
As acid and base reactivity. I'm going to put that in chemical properties, right? And this kind of applies with pH. pH is often used to measure acids and bases, but whether something can be an acid, whether something can be a base, we'll define those more this semester, that changes its chemical nature, that makes it a chemical property. Some things cannot be acids, they can be bases. Vice versa. Some things can be both, so that makes it chemical properties. Lizzie.
Like brittleness, like the malleability.
Do you think that's chemical? Does it change its
More physical.
does it change its makeup?
Yeah, no.
That would be one of its physical properties. So I'll put both brittleness and malleability. Did I spell brittle right? L-E?
I have no freaking
Yeah.
Thank you. And I don't know about malleability. I feel like that's a good guess.
If it gives off heat, would it be a chemical property?
If it gives off heat.
Yeah, like warmers, like the little like bean bags that you like crack to like warm up your hands.
So I think we're looking again at observations that accompany a physical change.
Okay.
But when I microwave my water to prepare for tea, it also is giving off heat, even though it's still just water. So temperature, I'm actually going to bring this one back up. Temperature is a physical property that can change. I can heat something, I can cool it without changing its chemical makeup. But if I mix two room temperature things together and suddenly one of them starts boiling, that unexpected change in temperature would be evidence of a chemical change. There must be a new compound that is releasing a lot of heat. So a lot of physical properties are observed when chemical changes are happening without necessarily making them chemical properties.
Thank you.
Did I have some more hands up? Anybody else wanted to add one? It's a whole world of things out there, right? Now, in the context of all of these properties, we can have this umbrella term that says if it differentiates, sorry, let me use the word distinguish. If it distinguishes one chemical from another, it is a differentiating property. Which means that it is totally case subjective. It runs on a case-to-case basis. So let's compare sodium chloride, which is your generic table salt, NaCl, from water, H2O. What would be differentiating properties? Edgar.
One is solid and one is liquid or fluid.
Good. So it's phase. its state of matter. That distinguishes salt from water. Ryan. Atoms that are in there. Now, can we say that's physical or chemical? I don't know. But you're right. The atoms do distinguish it. Its actual chemical makeup is different. I'm going to leave that one off because I'm not sure whether atoms would go under physical properties or chemical properties. Do you feel like you could lean towards one or the other? Yeah. So I'm going to leave that one because I think it kind of rides the border. Daniel.
Would that type of chemical bonds be one difference between the two?
I think that kind of lies with types of atoms that make it up, the chemical bonds that make it up. I'm not sure if that falls under its physical property or its chemical property, but regardless, I'm not sure it's one that you can observe just by looking at it.
I was gonna say taste, but I'm not sure.
I think taste would be pretty differentiating. Do you guys feel like salt and water taste different?
Color?
It's color. One is clear, colorless. One is white. Sadie?
I was gonna say temperature or phase change, so like boiling point.
Good. I'm going to put here just an abbreviation, BP temp, so boiling point temperature. Now that might kind of overlap with what we already said about phase change. Obviously, at the same temperature, they have different phases. Clearly, they have different phase change temperatures, but good to reiterate it. Who else did I have? Mark? Their texture is pretty different, huh? One is wet, and one is crystalline, brittle. That'd be a pretty good list, huh? Blake? Their smell. You know, I was thinking about bringing this one up. What does water smell like? Nothing really. But what does salt smell like? Salty. And that is kind of hard to say, but when I go camping, we bring a lot of little jars with our spices in it, and I had to label the salt and the sugar. Because salt and sugar, color is not a differentiating property. Salt and sugar, phase is not a differentiating property, while salt and sugar, their melting point and boiling point is a differentiating property. Their taste is definitely differentiating. Their texture is not differentiating, but their smell is differentiating enough. So I'll just crack one open and take a sniff and try to figure out whether it's sugar because it smells a little bit sweet, or if it's salty because it smells a little bit salty. But it's not easy to smell. It's easier to taste. Between water and salt. I don't think flammability is a differentiating property between water and salt. Does anybody agree or disagree with me that flammability would be a differentiating property? Has anyone ever lit salt on fire? Maybe. I actually don't think you could. Water. Has anybody ever lit water on fire? No, me either. So actually, these two chemicals are fairly inert when it comes to chemical reactions. Not impossible for them to react. They definitely do. But neither are flammable, neither rust. So I think in that case, would not be a differentiating property. Let's do Sarah and then Edgar.
I guess I don't know if it counts, but like the fluid of motion and how it moves.
Good idea. That would come with physical property, right? And I think, how could we try to put that into words? Viscosity is not quite right because solids aren't viscous. Viscosity describes fluids. So actually, I think I'm going to leave it off. I really like the idea. One is a solid, and so it just tumbles. One is a liquid, so it pours. We're going to talk about viscosity later in the semester. And one thing we know is that solids don't have viscosity because of their nature of being solid. So I think maybe we can just kind of put that back in with texture. Another way of describing its texture. Edgar.
I was gonna say, going back to flammability, the elements that make them up are extremely flammable, but once they come together, they become inert.
Yes, you make an interesting point. The chemical elements that make up a chemical have different physical and chemical properties from the actual chemical. So, for instance, we could do a comparison not of NaCl and H2O, but we could do a comparison of H2, elemental hydrogen, hydrogen gas, and H2O. And H2, incredibly flammable, H2O, the product of fire, and also something that can steal the energy from fire and quench the fire. So the elements themselves can have very different chemical and physical properties from the chemicals in those elements in different contexts in chemicals. Absolutely. And Brian.
What about density?
Sodium chloride and water definitely have different densities. Do you suspect which one would be more dense?
I would say it depends on the context.
Okay.
That's a cop-out answer. But
No, actually, it is a good answer, but you're going to have to expand now.
well, it depends, like, what type of, like, maybe if you have an external pressure force, I don't know, it might make water more dense than the sodium chloride.
Let's say they're at the same pressure then.
I'd say salt because it's a solid, water's a liquid, and then if you put salt in water, it also sinks.
Touche. Salt in water sinks, which is pretty good evidence that salt is more dense. I guess I was going to say if you have a large enough sample size, those salt crystals can actually be pretty far away from each other. You can have holes, pores that run past the crystals, right? So that creates a larger amount of space where the mass is actually spread out because there's air taking up some of that space. And that might make it look like salt is less dense. But if you could squeeze out all that air and just push all the crystals next to each other, then you'd probably get something more dense. Okay, that was a pretty good exercise. I want you guys to recognize differentiating properties are subjective. They depend on the scenario. The same differentiating property between two chemicals may not be a differentiating property between another two chemicals. Good? All right, I want you guys to actually get up and take some time to move around and get your blood flowing. Let's try to take about 5 minutes, and let's be back here by 1/4 after at the 3.
Sorry, I guess I should add this is very good. How much are you trying to have like the real chem checkpoints line up with what we're doing in class? We're trying to like
Very close.
pretty close.
Yeah,
Okay.
so-
maybe, like going ahead on it. Or like already.
No, feel free to go ahead. Absolutely. I think that
Just because the due dates they were like all due for like this week, and it feels like we're probably taking a little longer than that. I was
Yeah.
just wondering. 'cause,
And
like,
I'll-
first
I'll-
week, you know.
I'll look at seeing if we can push those due dates again. But again, it's because Real Chem doesn't know that we missed our Monday class.
I just wasn't sure.
2 weeks.
That was just like the first week or so.
And I'll send an announcement at the end of this week saying what I hope you guys have accomplished and what I think you should be looking towards. And if you're ahead of that, great. Yeah, no harm with that.
Thank you.
Thanks, Ian.
And John, density is the physical property, right?
That's right.
Okay.
Yeah, density would belong up here. Oh, that's not mine. Somebody said density, I think, right? But I never put it up there. rooms spying on our lecture. I don't think any of you guys can see, but there's someone in there looking. From my side, you can see her.
Well, why do you want to become a CRNA?
I had anesthesia because I got to do this. You work at you said?
Yeah.
Okay, well, you said CVICU? Yeah, I said I'm good at that. How long have you been ICU?
A little over a year. Well, I started at LB. Yeah, I was in a medical ICU and I switched. So I've been upstairs.
Did you go straight to ICU? Dude, you guys need to do that. And now you have to maybe get med surg.
Yeah, I get-
And I don't want to do that.
Don't do it. I always tell new grads to like start where you want to start. Don't listen to like the whole oh you gotta do this many years on med surg. I hate that crap.
Yeah, no, I went to the ICU, guys. I feel like it's the most thrilling nurse.
Yeah, like if you know where you want to go, just do it. I don't like that philosophy.
Yeah, my uncle's a CRNA. I'm West CRNA all day. I guess I see both worlds. I thought I wanted to go to med school. I don't do that and she did.
I can definitely give you advice, like, but I would say, yeah, it's a long road. But you can start in ICU though.
I want to so bad. I don't want to be starting med surg or anything like that. I have to move out of this state. I feel like nurses in ICU are super complicated in this class. Because all the nurses I know, like, they say they have coping.
Yeah, it's funny you say that because like I remember I had like 6 months maybe at LE and I tried interviewing at shock trauma, CICU, and they're like, oh, we got applicants with more experience.
And I where you were, did you learn high school? You were? All of them trying to find out. But my department is different. Yeah. Oh, they did? We nothing for a year.
They're stupid.
Oh, you do? Instead of waiting a year,
So, like, I guess how.
I would say though too, like one piece of good advice that I got early on is try to enjoy nursing. Like, you know, sometimes it's easy to think about like the future being a CRNA, but it's good to be present in the moment too, and like learn to be a competent nurse and all those little intricacies.
no, I think I really like everything about that. Like, a lot of meditation.
Yeah.
Yeah, so I just moved it outside the container of the and I try to lick the fish through the plastic. They'll like stack on each other and then start like choking like
Who got there in their science?
and it's like, guys, there's multiple parties. You don't all need to
Yeah, it
be
could
in
be.
the woods.
I would say though, like
And then
I would say try to get your capstone too in an ICU. I feel like that helps.
next day Spirit's like totally she thinks like, well, she was
We'll see what happens. If I have to move out of state, I can move still. Yeah, usually it's pretty complicated. Yeah, it is.
so
Have you done some shadowing with this year?
I gotta do you take yours?
I'm like, I'm trying to apply this year, but obviously, you know, chemistry, a lot of schools require it. And some schools, they don't, they're not as exclusive.
Okay.
So I'm applying to some schools, just put my name out there. If I get an interview, great. If I don't, great. Just trying.
All right.
I just, at the U. Yeah.
One thing I wanted to address about notes again, I know I'm recording them, but if you guys ever want to stop and take a picture, feel free to. And if I'm moving to erase something that you want a picture of, just let me know, shout at me so that I don't erase it. I also have kind of an odd way of organizing my indentations, I like my arrows. And sometimes my arrows point at a header, sometimes they point at a subheader, sometimes I've got these little down arrows that point at a subheader, and then sometimes I've got those bullet points. I do my best to keep a system, but I get screwed up sometimes, especially when I'm like several pages into an idea. I kind of forget where I had an arrow or a curved arrow or a bullet point. So I want to encourage you guys to copy notes, whatever feels best for you. Maybe you like to have one A, I underneath all of those things so that it feels more organized. Maybe you like to just let it flow and be a little chaotic. One thing that is really useful at remembering and retaining the information from class, and I know this sounds like a lot of effort, it's to take the notes that you got in class and rewrite them after class. That way you're spending more time with the material, you're thinking actively about what you saw in class, and you're processing, how does this connect together? How should I have it actually organized? I told you guys that I had professors that gave really good notes in college. And before exams, I often would just take my notebook and just flip through the pages because it read like a textbook. It read like a magazine. And I could just skim through and recall that information. But something that would have helped me even more would have been rewriting all of it, re-entrenching it in my brain. All right. Yes.
I found it really helpful, since I'm repeating. I'm a repeater, guys. I would leave 1 to 2 blank pages at the end of your notes. And when I would go through RealChem, I found that I added to each unit or module from things that weren't in the notes or things that I found helpful to when I would go through and do my homework. And those things became helpful on the unit tests.
Pro tip.
And
Leave space after my notes for you to contribute your own notes from your reading. That's great.
Yeah.
I will say my notes are taken from RealChem, but RealChem is a live textbook, so it's constantly being modified and changed. So my notes are from a year ago, and it's possible, I think even when I checked this morning, some of the pages have changed a little bit. And so it's never a bad idea to leave space. I try to summarize what I think is the most important concepts to present to you in a format that looks different than RealChem, but follows the same flow. But I think that is a great idea. Leave some space. What else did you want to add? It helped you on the unit test, you said, to have that extra material.
I just found like small things on RealChem that were like good for my brain.
Good.
So, because science is my worst subject. So, anyway.
We'll see if we can change them this time. Awesome. Thank you, Kristen. All right. So on the topic of these properties, differentiating properties in relation to a specific set of chemicals can be useful for telling those chemicals apart. But we also have this idea of intensive versus extensive properties. An intensive property is something. Oh, you know what? I'm sorry. Property difference kind of lies on a similar grounds here. The examples I'm going to give you are intensive differences because we'll be using it to differentiate between chemicals. But it can also apply to the properties itself. So it might be better to put intensive differences here, since we're talking about differentiation. But it's not wrong to call it an intensive property. Intensive differences between chemicals are innate to the chemical. Doesn't matter how much of it you have. An extensive difference and an extensive property simply depends on how much you have. So, there was a physical property we didn't put up here before, that was density. But we talked about how density can be a differentiating property between this. Is density an intensive difference between chemicals, or is it an extensive difference between chemicals? Intensive? So can you give me an example of how you can prove it's intensive? Maybe even use the idea of sodium chloride and water.
Can I use the example of where something sensor blue?
Yeah. So if you take one crystal of salt in a big tub of water and you drop it in, the salt crystal falls to the bottom. So its density is heavier. The salt has a higher density than the water. Now you take that same crystal and you put it in a little cup of water and it still sinks. It doesn't matter how much water you have, the density of salt is always larger than the density of water. Intensive. You see how it doesn't matter on the amount? So density, intensive. That's just for example. Color, intensive. Doesn't matter how much you have, that compound should still have the same color. What else might be intensive?
Just out of curiosity with that, so water is clear, right? But if you have a bunch of it, it becomes like a bluish color.
Does it?
Thought it did.
Does water
It
become...
looks, I know, I thought it looks more like that. Isn't it just like the reflection?
The ocean looks blue because the sky is reflecting off of the ocean, and the sky is blue. And the sky is blue because blue light scatters more than
So
longer
it's
wavelengths.
specifically light, not necessarily.
So if you have a giant pool inside of a closed room with no windows, and the walls are painted white, and the floor of the pool is white, your water should be very clear.
Really?
Absolutely. Water is not blue. It's strange because we all think of it as that. Take a glass of water at home and notice how it's clear, and then draw a bath tonight and look at how the water is clear. So that color is intensive. Doesn't matter how much you have, it's clear. But it can have effects from its surroundings.
And if you think about it too, like if you go to the bottom of the ocean floor, it's like black because the light has, I don't know, can't reach.
Light can't reach there, yeah.
That I got, but for some reason I was just like, oh yeah, more of it just shows more.
No, I get it. And I would say color is kind of an odd one because there are some chemicals, like gold, that if you break the particles down into small enough chunks, they actually interact with light differently and they change their color. So gold nanoparticles of different sizes appear to have different colors because of how they interact with light differently. So color is mostly an intensive property, but sometimes, like with gold nanoparticles, it does matter how much you have. And now I'm going to confuse you because when you go to do the Module 1 checkpoint, they're probably going to have a question that says, which of these is intensive, and they want you to take gold, or color, because they don't think you know about the gold nanoparticles. But again, this is us just trying to set our arbitrary lines in the sand, and nature saying, I've got an exception for you. Other properties that are always intensive, Daniela? Texture, pretty intensive.
Question, in that case, can we say that most physical properties are intensive?
No, because there's a physical property we didn't put up here earlier that I want to add that is a very common example of an extensive property. Can you guys think of an extensive property? There may be one here, but there is certainly one that's not here. Yes. Say it louder for us, Daniel. The mass that your chemical has. Or in other words, its weight. Extensive property. So I could say I have a gram of sodium chloride and I have 20 grams of water. That differentiates my salt and water. They've got different masses. That's a physical property. Doesn't matter how much, it doesn't matter whether it can chemically change or not. It has that mass. That is a property it has. It's its physical property. But that is extensive. I can take 1 gram of sodium chloride and just add more until I have 20 grams of sodium chloride. So mass would be an extensive difference, an extensive property. It depends on how much you have. Most of these other ones are intensive. So another example, flammability. Intensive or extensive? Intensive, innate to the material. If I take a scrap of paper, can it light on fire? And if I take a phone book, can it light on fire? Not as easily, but it can. So flammability, chemical properties, also intensive. Mass is kind of the outlier there. Depends on how much you have. There are other things. There are other properties. We'll come back to them later in the semester. Things like heat capacity is an extensive property. It matters how much you have. Okay? A little talk on purity before we talk a little bit more about phase diagrams. So let's define a pure substance. Can anybody put a definition to this? Edgar.
Neon.
I think that's an example, but not a definition.
Okay. It's not mixed. Neon exists on its own in nature. It doesn't normally mix with any other elements. For example, water is a combination of 2 elements, right? And salt is the same. Neon just kind of floats on its own, and it doesn't really have any intention to mix with other elements.
And I think maybe you're getting the ideas of bonding and mixing a bit conflated. So neon, for instance, in a neon light, I can crack that light and let the neon escape. And now it's mixing with oxygen, water vapor, carbon dioxide, nitrogen in the air. And so the neon can mix, but it's not bonding with the the nitrogen, the oxygen, the carbon dioxide in the air. On the other hand, water, despite having 2 different elements that it's made up of, can also be pure, so long as water is the only chemical. So a pure substance has only 1 chemical. Does not matter what that chemical is. And remember, a chemical doesn't need to be a chemical element. It can be a combination of elements that we now describe as a new unique chemical, like water.
So it'd be wrong to say a pure substance is a substance that cannot be broken down into, because you can break down water, right?
Absolutely.
Okay.
You can break water down into more fundamental components, but that's not what makes it pure. Just that it is a substance, a sample that has only one chemical in it.
I just like the idea how they describe in the book that pure substance is something which you can wake up only without any chemical reaction. Or the opposite thing, mixed substance is something which you can break down with using some chemical reaction. For example, if you take milk, you can filter it or do something else,
Mm-hmm.
add acids or bases to separate the something which is inside. And if you take water, without any chemical reactions, you cannot separate it or divide it into hydrogen and oxygen.
Good. Okay, so I want to try and see if I can repeat that. So a pure substance can only be further broken down by chemical processes. There's no separation that can occur because it's all uniform, just one chemical. You would need to break bonds in order to separate it further. Whereas mixture can be filtered or can have a chemical reaction added that separate things. And that there is a difference between this idea of inherently pure substances that are made up of only one element, in addition to a pure substance that's just one chemical. Okay, so pure substance, only one chemical, mixtures, at least two chemicals. And in these mixtures, we talk often about impurities. Impurities are these chemicals that are found in small amounts or in low amounts. And I'm using an arrow there to indicate those are the chemicals in low amounts. So let's come back. Can we build a list of pure substances?
Water.
Water. Saint?
Gold.
Gold. Gold has this chemical symbol AU. So I'm just going to put AU. Examples of pure substances. Mm-hmm. A lot of metals.
It's on the periodic table.
The whole periodic table, good. You could just have the periodic table. If you took each of those individually, you'd have pure substances. In addition to a ton of different combinations. Diamond can be considered a pure substance because it's all the same chemical composition throughout. What about mixtures? Can you give me examples of mixtures? Salt water. Because now you don't have just H2O, but you have H2O with NaCl with all sorts of other things. For instance, take seawater. You don't have just H2O and NaCl, you also have microorganisms and seashells and sand. So you have a mixture of all of these different things. What else?
Baking soda.
Baking soda, to my knowledge, is mostly sodium bicarbonate, NaHCO3. But do you guys know, is baking soda mixed with other things?
In the US, we always mix it with aluminum.
Aluminum.
It's or baking powder.
Baking powder, I think, is a combination of things for sure. Baking soda might be a pure
It says pure substance.
substance.
Sorry, I have a question. With H2O, how is that a pure substance? Because it's a mixture of hydrogen and oxygen.
The chemical is a combination of two hydrogens and one oxygen. But that is the chemical. And so if all you have is the chemical H2O. You have a pure substance of H2O.
So, okay, so that's the one.
That's your chemical. Yep. This has matter. It takes up space. It is a chemical. And if that's the only thing present, it's a pure substance. Now, how many of you have probably ever drank pure H2O? You think so, Sarah? Where did you get it? Distilled water. Deionized water. If you drink out of your tap, even if you drink from like a Brita or a zero filter. Anybody have a zero filter? I had one of those for a while. It actually gives you a device that measures the parts per million of solid particulates in your water so that you know when to change your filter. Those often let some amount of ions through, which is good for your body to an extent. You need some of those ions. But distilled water is designed to remove all of that. And yet, most distilled water has some other chemicals in it. So even the best distilled water might have a little bit of other stuff. Upstairs, we have distilled water in the chemistry lab that is 18 milliohm water, and that's about the purest that we can get, and it runs through like a double salt ion remover filtration system, and it's challenging to get truly pure water. That's about the closest you could get. So I think baking soda, we decided, is a pure substance, but baking powder is a mixture.
I have a question. So with that logic, would that mean that sodium chloride is also a pure substance if that's all you have?
Correct. So baking soda, by the way, NaHCO3, that's its chemical formula. And by the same logic, sodium chloride, table salt, is a pure chemical. But again, if you look at the grocery store and you're buying iodized table salt, so that you get iodine in your diet, iodine would count as the impurity, and it would make it a mixture. So impurities, I'm going to say iodine in table salt. Most of the table salt you buy is probably not actually pure. It probably has some mixture of other chemicals in it. In fact, pure substances on Earth are so incredibly challenging to get because molecules, atoms, are so tiny. And so to prove that you have pulled out every single molecule of a different chemical, it's almost impossible. So a lot of things are mixtures. In theory, things are close to being pure substances. Yeah? All right. There is another conversation on this, but we're going to actually talk about it when we talk about the scale of chemistry. And that talks about homogeneous mixtures or homogeneous substances and heterogeneous mixtures and substances. But we're going to talk about it in the terms of scale because something may look homogeneous from one scale and heterogeneous from another scale. And so we'll come back to this idea of defining purity a little bit more. For now, I want to transition us into states of matter. And it's from here that we're going to talk about phase diagrams. We said that this was what type of property? Physical property. Because it doesn't depend on a chemical's ability to change its chemical nature. And would you say that a phase of matter can be differentiating? Can it be a differentiating property? Good job. Yeah, absolutely. It can be a powerful differentiating property, but you want to differentiate salt and sugar, phase of matter doesn't help you differentiate. You want to differentiate water from rubbing alcohol, the phase of matter doesn't help you differentiate. When we talk about states of matter or the phase of matter, we're often talking about normal conditions. And that means 25 degrees Celsius and 1 atmosphere of pressure. This would be the temperature and the pressure, T and P. We're going to look at phase diagrams where we change the temperature or we change the pressure, and we see how the phase of matter changes with that change in temperature and pressure. So first, some quick definitions. Solid, which we'll abbreviate with S. How could you quickly define a solid? Good. Rigid, with constant shape. I bet you can find some exceptions to that, right? Because the tip of my marker is solid for sure, wet with ink, but when I press it onto the board, it changes its shape. So maybe we should actually say constant volume, or maybe there's some better definition, but this is a good way to first approach it. It's got a constant shape, like your desk, solid. Liquids. How could you quickly define liquid, which we'll abbreviate with that L?
Take up the shape of its container.
Good. It does take the shape of its container. So liquids will flow, and because they take the shape of their container, it's hard to say what's going on with them. So what we can say is that they have unchanging volume. Whether I have some water in my water bottle and then I pour it into a vase and then I pour it into a pitcher, it's going to take the shape of that pitcher, but it's always going to have the same volume, the same amount of space that it takes up. And then gases, which we'll abbreviate with G. What can we say about gas?
No definite shape or volume.
Good. Now, we can write no definite shape, no definite volume, or a way to characterize it, we can say that these expand and compress to their container. The shape depends on the container. Its volume depends on the container. Our phase diagrams. Plot pressure versus temperature. So along my y-axis, I'm going to put pressure, and along my x-axis, I'm going to put temperature. I don't have units, and that's because this is a bit arbitrary right now. But all good graphs should have units. The unit of pressure, the unit of temperature. Are you reporting Kelvin, Celsius, Fahrenheit? Are you reporting bar, atmospheres, pascals? Those all are important to show. But generically, a phase diagram looks like this. Your textbook actually shows a phase diagram and all it has is a bunch of different dots at different pressure and temperature combinations. And then those dots are colored based on the state of matter it has. Most substances follow something that looks like this. It's kind of like this curvy Y. Now, at these incredibly high pressures and incredibly low temperature, what state would you expect a compound to have? Low temperature, high pressure. Why is solid the idea? Perfect. The pressure is pushing it in. And the temperature is low, so it doesn't have a lot of energy to move around with and escape. This is our solid region. What about at very, very low pressure and very, very high temperature? What state do we expect here?
Gas.
Can you tell me why?
I can't tell you why.
Well, like Ryan said,
So yeah, it's the same thing. So since there's low pressure, it can kind of expand, fill the container, and then gas is more like spread out.
good. We know that gases expand to their container. So if there's low pressure, if there's not something pushing down on your substance, then that means your substance is pushing out on itself and it wants to change phase and become a gas. And at high temperature, your substance has a lot of energy to move around with. So low pressure, high temperature, we've got our gases. What takes this middle category? Liquids. Moderate temperature, moderate pressure. So I want to put two phase diagrams up here that look similar to each other but slightly different. And I'm actually going to put some units on it this time. On the left, I'm going to kind of zoom in on the graph. And about halfway through my y-axis, I'm going to put 1 atmosphere of pressure. And then over here, I'm going to put 80 degrees Celsius. And then I'm going to repeat a similar graph that's a little bit less sloped, about halfway through 1 atmosphere. And then right over here, 100 degrees Celsius. Just for clarity, I am zooming in on the part of our graph that's about here. So can you tell me above the black line and below the black line what phases I'm looking at?
Well, above the black, you're looking at a liquid, right?
How do you know?
Because you're scaling the larger picture.
Yeah, and above that larger picture was liquid and below it was gas. Let's reason it out using temperature and pressure again. As I move up at a constant temperature, as my pressure increases, I go from a gas to a liquid. Constant temperature, as pressure increases, I move from gas to a liquid. So look at this constant temperature. As I move up in pressure, I should expect change from a gas to a liquid. So up here, liquid, down here, gas, up here, liquid, down here, gas. And I'm looking at this intersection, actually. This intersection at which a compound transitions from being a gas to being a liquid. For both of these, the transition we're looking at is at 1 atmosphere, but the temperature for that transition is different. Which of these compounds is water?
The one with 100 degrees Celsius.
And you know that because I told you?
I read it in a book.
Water boils.
We know that water's boiling point is 100 degrees Celsius. Its boiling point is a physical property. That's the phase change from gas to liquid. I'm sorry. From liquid to gas is its boiling point. So, two ways that we could look at this. If we have a constant pressure and a very low temperature, then I will have a liquid that is increasing in temperature until it reaches 100 degrees C, at which point, at that constant pressure, it transitions into being a gas at more than 100 degrees C. Or I can look at it another way. I have a gas at 100 degrees C, and I am increasing the pressure on it. As I increase that pressure, the gas starts to condense until at 1 atmosphere it becomes a liquid. And then it stays a liquid of 100 degrees with higher and higher pressure. That's how phase diagrams are meant to be interpreted. Pick a constant temperature, see how the pressure changes. Pick a constant pressure, see how the temperature changes, and notice how its phase changes along that change in temperature or pressure. All right, I've taken you guys to time. We still want to look at chemical equations and scale and types of energy before we're done with Module 1. I think we could have gotten through it all today, maybe, if we didn't take that time to get to know each other. But you guys as a class need to know each other. I want you guys to be able to build relationships, build study groups. So I wanted to take that time for you all to get to know each other. When we come back on Monday, we will be quickly finishing up Module 1 so that we can get into Module 2. If we don't finish Module 2 on Monday, there's a chance we won't. We'll definitely wrap it up by the end of next week, which means that you should be getting prepared for a Module 1 checkpoint next week, as well as a Module 2 checkpoint next week, which means getting ready for a Unit 1 checkpoint next week as well. So be looking ahead for those 3 assignments. Try your Module 1 checkpoint now. Maybe you don't need to wait on me for it. All right? Have a good weekend, guys. I'll post another update this weekend about where we're at and where we're going. I'll see you on Monday.
Just to ask real quick, the sign said no food, so no food in this class, right? Or do you care?
I don't see that sign. I don't know what sign you mean.